Okay, so I've got myself fully set up on Linux now. Here's my Debian desktop to prove it. And so I'm gonna be testing that out today. I've got it just barely set up with 4Coder, Clang, OBS, so I can record, and the basics of my projects so that I'm ready to build and run the C scripting repository right now. And what I want to do is build out a better example in the C scripting repository. Right now, all I have is this file, this pair of files called example1. And it's just very basic. It does not show anything particularly meaningful besides the boilerplate in action a little bit. Um, so I have an example idea that I want to build first. Something a little bit more meaty. This might be a more complex one. It might not be one of the examples that I have in as sort of a getting started example, but rather it's an example of a rather useful pattern you could put together, and that's a stack machine. So um, let's see here. C scripting example, stack machine. We're going to get there in steps. Let's start off by just getting the right includes to have an example. So symbol set stack machine.h standard.io.h. We're going to need an int main at the bottom. Let's see here. Is there anything else from the template example? So I am going to need to build up a little bit more of a pseudo base layer here. Right, something like this. So then this becomes this, plus we're going to need to add Arena. Oh, I haven't set that up yet. Let me go add something to my 4Coder config real quick. cc build config not set down. Okay, hopefully I've got everything configured on this one now. Cool. So I'll come back to that. I don't want to get bogged down on it first. I want to sketch out a little bit more of the example here. I also need the I guess we'll start off simple, right? Start off simple. So the stack machine, it starts off as a state machine. That's the first version of it we build. So it goes like this: state machine, stack machine, stack machine plus frames. That's the plan. for today's example. And this video will serve as sort of the example too. I'm kind of explaining it giving my best effort to explain it in this video. So we're gonna want each state to have something like a display name, or we could just call it a name, I guess, and function. For now, there's nothing in the context, but that's how you get it started. Now, let's see. If you want, if you want to define one of these, we're then going to copy this. Instead of x1 command, this becomes a state machine state, and call these the states. And the type is sm state. Okay. That boilerplate sets up my sections on each tool chain and the ability to locate them with this. And it also sets up the type with this, right? And then this header here does the work and clears out the definition for this at the end. So that the rest of these definitions, by the way, they stick around, and this becomes the way of referencing this bundle of information, this name here, right? So then what you do is you have something like, I want to be able to define a state. I often write it like this. You can also just write it like this, though. Give it a name. It doesn't have any other properties yet, so it's going to have a function. I'm going to name the function with the name from the symbol here and type it that way. So it's going to match the state from the type. Then I define an SM state, and I use n, the name here, to define this. So this becomes a global variable and also a symbol, right? It defines a symbol that is literally a global variable from C's perspective, but it's arranged inside of a symbol set so that it has an ID and it has state. Well, it mainly so that it has an ID and it has the ability to be indexed to find its state. Right, it can be iterated, I guess is what I'm trying to get at. So I want to give it a name by writing something like and then I'll add that up here to the pseudo base, the little mini base thing that I've got going. So this is just going to be U8S, size of S minus 1, U64, and so rate const sm state const 10. Then we do this function again so that the person defining the state can now put the body of the state function after. And so this chunk here defines my state types, my state symbols. Okay. I hate this thing. I'm gonna just do this. I'm gonna just do it like this. It doesn't sort out nicely the way everything else does. Okay. So for this one in particular, I may want another helper. I don't often need this one, but for state machines, I find I just prefer it because of stuff like this, where I want to reference a state before it really comes in the definition order. So this could look like sci declare. And what declare does is just what the C idea of declaration always does. It lets you name a thing that's going to exist and start referencing it and defer the definition to later. So here I can define the state location, and then here I can give it a body, right? Like here we know it's going to exist, we can refer to it here. But now goes like that. Right. So we set the context ID like that. And we'll say as long as the ID is not 0, actually it would be cuter to get this. Then what I want you to do is get me the SM state sci address from ID of context state ID, right? So the state ID is a variable. I can use this macro, and what this basically does is a little pointer arithmetic off of the base pointer of the symbol set, right? It's not as fast as you would like because this is the checked version. So if this is ever not valid, it's figuring that out first. But it's close to just pointer arithmetic. And if you wanted to, you could do unchecked. And then the only downside left is that it is 1 based. And so it has to maybe do some adjustments based on that. Although sometimes it also has to do, if you're on Windows, that adjustment cancels out with another one. And so in a way, it's even better. Although it's actually worse. Anyway, it mostly just works as a pointer arithmetic operation plus a tiny bit of arithmetic, but it's not as low level optimized as you would like. And then, at the limit, it's not as optimized as you would like. And so then what you do is you go call that function. You go, first of all, we say like, hey, if this equals 0, then we actually have like an error behavior and break. But normally what should happen is we get the function and we're going to call it with the context. Then we have these context functions. that make this API for the scripts to access, right? And let's implement those. So here's our symbol definitions. And here are some of our regular function definitions. Right, and of course we have our entry point. But our function definitions are just these things. Right, so right now, when I look at this example, there's all these different ways of building. The first example, example 1, I'm gonna need to be able to change and build multiple examples, but I also have so many scripts right now. Build sh is build with Clang. I have build with Clang and build with CL in sh and bat formats. So all these build scripts are for building the basic example, and I don't know if I want to make that a parameter. If I made this a parameter, it's I need to rename this one. Build rename file query build with Clang sh. The project file build sh. We'll make that build with Clang actually. Okay. Right. There we go. Let me just test something out here. P1. Isn't it like... Okay, and so if I were to build with Clang space stack machine load project. Okay, so why don't we do it that way? We'll say if $1 equals blank, build the first example. If these probably all need spaces if I'm remembering correctly. $1 equals stack machine did this work before? So let me go look at something like BLB core. Surely I have an if else in here somewhere. Okay, if this, then elif, then frustrating. Okay. Do it like this for now. We'll do it like this for now. Okay. So run sample one. Sample one with stack machine. Load project. Hello world. Okay, so our state machine is working. So let's go back and talk about that now that I got it all set up. So we have a state machine. You initialize it by giving it some state. Each state can do some code, whatever it wants. And it can also talk to this API, SM state next, SM state done, to either pick a next state or to end the loop, right? And so now you've got yourself a state machine. And if you want to, you can build other things that happen here. So for instance, one cool thing about having a state machine is you could have a debug mode. That goes something like this. So we've got the state that we grabbed from this. If we have diagnostics enabled, then show us each state as we execute it. I don't really think that's going to work better. Let's do it this way. Now, of course, when what you have it doing is printing to the same stream as the main thing, it does not look quite as nice because this, right? But we could say, like, what if this wasn't printing to the same stream? And then you'd see, like, this gives you the log of what states you've entered. But if you're gonna be generating output from the states that it doesn't know how to interleave itself properly, like here, for instance, if these always had new lines, for instance, then you wouldn't have this issue because each line could just be part of a different sort of stream. Then you'd be okay. But you get the idea, right? Like you can throw in something like diagnostics. How can I improve the example of a state machine just a little bit to make it more interesting now? So it's not printing hello world, but doing something else. Build a little, build a quick little game out of it. text. It doesn't really work properly, does it? Now that I think about it. Better to just do it this way. Okay. What's that horrible function? This one here. I want this and this. So give me scanf, printf, the board. All right, so it should start up, clear the board, print it, ask for a move, set the move, pop over here. Now, real quick, we gotta figure out then when is the first rule. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 lines to check. Okay. Lines I dot index j equals O. Count my plus equals 1. Else blank spot equals 0. Get to the end of that, if the blank spot is not uninitialized cell and count of mine is exactly 2, then x equals index mod 3, y equals index over 3. Block, then block. Other equals 2 and blank spot is not null. Otherwise, just random. Okay, so that's all good. Then the only other thing we need to do is a little And then these can just do something like if right, and then we go P1 bin, lose. Blank spot not index is the name I should reference there. Lines, tic-tac-toe lines. Okay, so I should be able to do something like build slash stack machine. Should be able to play. Let's take the top left corner. Take the top top right corner and the middle. And so now the diagnostics look a little nicer, right? We can see, oh, we started and we knitted. I got to turn P2 turn, and then if I turn these right, you can see all that. And if I turn the diagnostics back off, then you get, you know, your state machine up and running like normal. Opponent seems to have played it 1-0 after me. That's a little bit unfair. Don't mean to turn this into a tic-tac-toe programming day, but just want if I can figure out why it would do that. I played it 1-0. The board should have an X there. shouldn't be getting a blank spot. So it thinks it can win. It's not allowed to play this spot. Huh. Huh. Would it do something different if I did this? I'm curious. It did indeed. Do something different. I'm not clear on how it's calculating need to block twice right here. But it's cool that it blocked me there. But I feel like there's still something pretty wrong. Let's try picking its favorite starting spot. Yeah, so it just still thinks it can play over me anytime. Block. Those can go away, but blank, then that's potential. Ah, this needs to be going potentials index, right? Not just take the index, but the potentials index. That could get you some explanation. Now, what about the lines? Are the lines correct? Double check. 0, 1, 2, 3, 4, 5, 6, 0, 3, 6, 1, 4, 7, 2, 5. All makes sense. Those are the vertical lines. 0, 4, 8, 2, 4, 6. Those are the diagonals. I mean, that's just pretty easy. I don't see how that could be wrong. Oh, crap. Okay, there we go. My bad. Can't run this one from here since it uses scanf. It won't work. Okay. Nice. Okay, cool. Cool. Why was it saying that yeah, I mean, there's probably still a bug in there, but I'm not quite sure how to pull that bug out since I have fixed the other ones. There was something weird about how it thought it could find more than one place where it needed to block that one time. Anyway, so that's the state machine part, right? Hopefully the basic idea here makes sense. You can set up things like diagnostics or even not just debug stuff, but like actual semantics that you want to associate to your state loop somehow, do some kind of setup and cleanup automatically on it, whatever. But I want to take it a step further. So state machine done, but the next step is to make it into a stack machine. So in a stack machine, instead of having a single state ID, the idea becomes to have a stack of them. Now this is where I'm going to need to set up a little arena because I want to do it like I would, roughly speaking. And so we're going to do a really basic arena to get us started. I'm not sure for what kind of like popping I might need yet for the arena. I'll probably end up just wanting like a little base layer that that I can reuse between examples. Kind of feels like. So then once you've got an arena set up, say you've got it like this. Then you can eliminate this logic here. We're gonna need and you can just go with like a starting point of a node structure for your stack. Right? You can do other ways, like you can make an array of state IDs. But if you want to have no cap, if you want it to be able to grow arbitrarily without you having to think about what the cap should be, then an easy place to start is with a node. And then you can switch it out to like a buffer index system once you've developed the idea more fully. But this is the easy way, right? And so then you give the state ID to the node. And you also have, you can do this a couple different ways, but you have the option to say something like this. And so I guess what we'll do is we'll say one of the things the arena should be able to do is pop to. All right, that's simple. Even that simple, but the ability to pop to pop position, so we'll make that like this. And then this expands. You have state next, gives you the next state at the current level in the stack. Next push gives you a next state ID and a push state ID parameter. And the reason you do both and not just one with this sort of thing is because you can only have one state transition. You want to simplify it down to just saying we're going to have one state transition per state, right? So every time you run a state, you should get a state transition. That could be next, which tells you go to the next state. Or if you are going to push, then you need to also tell us when we pop, where do we go after the pop, right? So the stack lets you put something else on top, but what's really important is the thing you remember underneath for later, right? And the thing you remember underneath for later is where you go next. So that's what the stack push looks like here, is we set a next state for the current level of the stack, plus we push a new state that goes first. So this will go first. When this state pops, that'll go to here, right? And then instead of this done, we have a pop, and the way you end, the way you replace, so done is gone, but if you pop and empty the stack, that is the new version of done, right? So these all stay the same for now. But these change. So next no longer sets this. Instead, it has to go in and say, okay, if the context stack is not empty, then this pointer is the top of the stack. Set that as the state ID, right? And then next push looks like this. And so stack So we are also going to have... No, we're not going to have a free list. This is what I keep getting confused about. The reason we're not having a free list is because we're using pop positions. So we actually don't keep around nodes from the stack and reuse them. Instead, we pop the arena. But if we wanted to share this arena with other systems, like if you wanted one arena that was going to run your stack and your entity nodes and whatever else, then you'd get in trouble, right? So you might have free lists because you'd allocate a stack node and it would have to stay a stack node because it's not the right size to be anything else. But I have tended to find that I like to use the arena. Like when I'm building a stack like this, I like to use the arena in isolation anyways, because like I was saying, the stack nodes, very simple way to get started. Later on down the line, you're probably going to switch to like a buffer-based version of this, and then you're going to have to isolate the arena for the stack anyway, and you're going to have some kind of growing in place logic and swap arenas or something, right? So it gets a little bit more interesting when you try to make it more performant anyways, so you might as well set an arena aside for it because an arena is a stack, right? I mean, that's the kind of it's a memory stack. And so a high level stack, like a semantic stack built out of these nodes, having under the hood a very direct sort of isomorphic relationship to the memory stack that is allocating it is a really nice way to do things. So let me show you how I mean that. So we say next push, then we still need the current to not be null because we're setting something about the current. And then we also need to be able to allocate onto our stack arena a stack node, and we need to give that new node the push state ID. What we also do is right here, we need our arena to expose its position actually. Arena position. So we remember the current position of the arena first. And then we save that into the node. So now if we want to pop this node off, all we have to do is pop to this position, which is the spot right before it existed, right? So that takes it off of the arena stack. And then there's just one other stack at a different sort of like level of abstraction, which is the chain of node pointers, right? So context stack points to the new node. So this basically says set this to this, but while you set this to this, remember everything else you have underneath, right? So if this is already a node pointer, new node now points its next pointer at what I had on the stack, and then the stack moves the stack pointer itself moves up to the new node, right? And so here we remember our position on the memory stack. Here we push some new stuff onto the stack, including how to pop all of that memory. And then we push onto this linked list that's organized like a stack that runs through this memory so that the node pointers link up, right? And then when we go to pop, again, this makes sense only if there's not, or only if there is a stack already, right? And what you do is you take a look at your current position and arena pop to on the stack arena the that position, right? So the position you're going to pop to comes from the context stack pop position, right? So there's where we're going to pop to. But before we do the pop, we also want to unthread that sequence of pointers that run, of node pointers that run through the memory, right? So at stack pop modifies the stack pointer again, and then arena position pop to, right? The pop to actually frees the memory. So these do a pop instead of a done. Oh, right. These are base layer features that I don't have over here. Let's go into the Mr. Forth code base. More and more. I just wish I had my base layer stuff. Stack push. Let's just grab all of the linked list macros real quick. Add them to the mini base over here. Give me 10 megabytes for this. Right. So we could also have some other stuff we want to be able to do, like these make the API for the state transitions themselves. But it kind of seems like we want this now. So this can go live there, and this can be like this. stack's not empty, it keeps running. Okay, that seems like about everything. This should work the same. It doesn't. Okay. Give me an idea of... I'm not used to this. Okay, there we go. No, that does not give me any idea of what's happening. Can you please just switch between this and this more easily? Do I have to fight it all the time? Okay. So, what's happening here? Content stack empty. Oh, I think this is backwards. Here we go. Okay, so this whole board check thing is a good example of where it doesn't quite feel right the way it's currently set up. Because I have this problem where I end up having to write this code and this code, which are the same, because I need them to run from different places, right? I want to be able to say, okay, at the beginning of the game, go to player 1 turn, but also if you are not sure how you got to player 1 turn, then you need to do a board check. So what we can do instead is say, what if we don't put the board check in on these states, but make the board check a separate state that we can push? That way, board check can be written once, and it doesn't matter, right? Because the other problem that happens is we need to check between every turn, because either turn could end the game, and either player could end the game by winning on their turn, and so we need to check the board between every turn, unless we wanted to get more fancy and use specific knowledge. But a generic easy solution is just between every turn we're going to check it, but we don't want to code the 2 turns the same way, right? We want to code the player turn this way, but the AI turn this way, or the bot turn this way if you prefer. And state machines make it a little difficult to abstract that by themselves, because you need some way to know where to flow back to. And so making something reusable like this requires this ability to say, I want to do this logic, and I want you to do this regardless of the way this fits into a bigger picture, right? I want to be able to paste this logic into different subcontexts of the whole and not have to copy the code around. And that's a part of what the stack helps us do. So let's use the stack to fix this. The way it'll work is there'll be another state called board check. And what'll happen is we'll drop the current version of board check, and we'll switch these out with next push and give it board check, right? And the same sort of thing will go on here. So here you'll say run the turn, and after the turn run a board check, and then go to player 1 turn, right? So the next thing we're going to do is player 1 turn after the interlude of board check in both cases. And then the logic of board check can be like, this is no longer a helper function because it can just be a state. cell. If any of these are equal to blank, then it's not a tie and break. So it is a tie if we don't have a winner unless there are empty spaces. And then if the winner is equal to 1, so if we have a tie, we have a case. If winner is 1, we have a case. If winner is 2, we have a case. Otherwise, and then some state pop. Now, how do I think this will work? So you run the board check, you figure out what's going on. Oh. So what needs to happen is that these still need to contain the control flow. That would allow them to pop. Because we don't want to modify the board or the stack from a distance. So something still has to be able to pop itself. Something else won't pop it for you. But then any of these conditions need to be like this. And maybe instead of having winning and losing as yeah, this also works. What if we just do it like this? So they're still states so that you can see them separately. But we do state next, context, side ID, SM state, P1 lose, P1 win, tie. Either way, those pop themselves and they set done, and then the game loop itself sees the done and also pops. Right? And so yeah, I tied. And then tie popped. It found it would have been doing a P2 turn, but it popped again. Right, so that's an example of how it works when you make it a stack. Now, the last step is to add in this idea of frames. And frames make it a lot more involved in some ways to set up. First of all, we end up needing a new symbol set. Each frame will come with a name for diagnostics and a size. SM frame, state with frame, okay. That sets up the frame C script. Let's also put in a definition helper here, frame F, but how do I really want this to work? So frame F is going to be a struct. And that's different from, okay, so this is like SM frame paste F is this. So we first type def it separately, and then we set the struct up and leave it hanging so you can define the rest. So this lets you write something like this. So you can put your variables on a frame. I don't think we'll want that. So let me see, how do I want to, I want to go through these in a couple of steps because there's a couple different features you can do here. So frame struct, let's do frame type def ft, and for that one you just do type def t sm frame f, right? So the idea is like the first one lets you type def as a struct that doesn't exist yet, and then you give it the struct. The second one lets you say something like frame type def tic-tac-toe equals, you know, maybe you have a tic-tac-toe board up type already somewhere separately, right? In a different header, you've got this thing already set up and you just want to use it as your frame. So that's what the type def version does. Either way, you end up with this name, the same name, SM frame, that matches the name of your frame, right? And then you can make the frame itself. This is like a side define SM frame F equals straight const the name of the frame, and for the size, write down the size of, and then the name of the frame type, right? So that's why you have to define this first somehow, and then you can do tic-tac-toe the frame. Oh, sec. And then, continuing, we want to change states a little bit to tell us which frame they want to be a part of. And so then this becomes a frame ID, so we know what frame it's a part of. And let's see, let's spell this stuff out a little bit more. Okay, so because this is a frame ID inside of a static initializer, I have to reference it as a raw first. So this is a frame, and F is the name of it. I'm sorry if I bumped the mic just there. Where did I leave off? So I'm referencing it with a raw initially, which means I'm going to need to set up sci-init. Now, I've never tried this before, using the one that's built into the symbol set with the extra header. Let's try this. Include symbol set init.h. That is supposed to get me set up. Ah, I didn't update this one. Okay, so we need to go back and apply this to this. Okay. New boilerplate is now implemented on the new init thing. Now what? Oh, it's not Mr. Fourth symbol set define. This should just be symbol set define. Okay. Too few arguments. What do you mean? Just pass it and nothing. There we go. Okay, I didn't test this. That's my bad. And this is tic-tac-toe, etc. But I don't want to do those yet. I want to stay here. I want to run a sci-init for sm state for sci each sm state fix up the frame ID. Frame. Right, so this one is telling it to translate raw ID from address. No, ID from raw in this case. Take a raw ID and convert it to a regular ID. And do that at init time when I call sci run init, which can go right here. Sci-init. I thought we defined this. Like this. Okay. No, we're not doing all that anymore. That really helped. Just do this. There we go. Tic-tac-toe. 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 Cool. So I set everything here as a part of the tic-tac-toe frame. There's a little bit of a problem with that interpretation, which is that board check is a push. And I said that when you push a state, you would also push its frame. But it's kind of looking like, at least for this one, it's sorting into a slightly different way, where you want to be able to push a frame and then push multiple levels of the state stack on that potentially. I'm not sure, but it feels like board check wants to read the same board that is being played by the steps below it. I'm trying to think of what I could do to make a better example of how this actually works out, because what I'm missing right now is a motivation for doing a frame struct with this little tic-tac-toe example. The reason I use frames ever is so that you can have a variable amount of information. It sort of feels like you need 2 games to even get close. But then this factorization into board check being a push is still actually not going to work. Right, like I could do a separated board check. So here's one thing I could do. I could go turn P1 turn, right? And so you go like let me just see how I could sort this out. So you'd go like this. You'd go straight to board check, and you'd set frame turn to 1, right? Yeah, there we go. So the frame will let me keep my state a little simpler in terms of its factorization. I don't have to use the stack to know where I go back to, because I can use the turn bit. Right, so they both have access to the frame by default, and we'll go through how that'll work, but the idea is board check doesn't want to pop in this case. Instead, what it wants to do is it wants to say, if the current frame has turn 0, then go to P1 turn. Otherwise, go to P2 turn, right? And like all of this is the logic of what you do if there is no end state, right? So these are the end states. This is next turn. board check is not a push, but these are still pops because they end the tic-tac-toe game. And then if the context loses its board and it's done, and all the places where we used to talk about context board is now frame board, okay, that looks good. Looks like frame didn't pop up anywhere it shouldn't have been, but it still isn't ready to build because there's no actual frame pointer available to these things yet. So the state function now takes, in addition to a context pointer, a frame pointer to tell it which frame this particular run of the state logic is supposed to access as its like frame context, right? So the reason we set up those frame types earlier the way we did is so that we can make these read the type off of F for the frame, right? So that looks like that, but you do have to cast this now because it won't be happy about the mismatch between the void pointer here, which is untyped, and the strongly typed one here. This is not a thing anymore. Now we have to give it frame data. Where will the frame data be? Well, it's going to be on the stack, so it's going to be more information that lives on a stack node. When we push, we will need to ask, hey, this state I'm looking at here, what's its frame? So here's we read the current position. We set the next state ID. We got to look up the frame ID from the, well, first of all, let's look up the state from sci address from ID, sm state push state ID. Then let's look up the frame. The frame is again address from ID, sm frame state frame ID. So this was originally a raw, and then it got converted into an ID when we ran sci run init. And so now I can access it. I can access a frame off of it like this, right? And then when I have pushed a new node, in addition to setting the state data and the pop position, I also push additional data onto the same stack arena based on the frame's size, right? The frame, as a reminder, contains its name and its size. And the size is the size of whatever type we use as the input parameter to a state function. So now what we're saying is the frame pointer, which is void and doesn't know its own size, statically was allocated from the frame size. So as long as the type that is expected here, frame F, has been encoded as the size into this frame, which it should be because this is the same exact one we set here, and we linked this state to that frame. So they should all be tied together, and therefore we should be getting an allocation here that is the right size for this frame. And as long as that is true, which it should be, this should all just work like this is just memory that's available to access is initially cleared to 0. Actually, that's a good point. I have not set this to implement clear to 0. And therefore, we should be able to go into our context here and get that frame pretty easily. Context get top state, context get top frame. And so then we can do something like it's going to look kind of like this. It's going to end like this. That's going to be like that. And then that's just going to be like that, right? The pop2 already frees this for us on the arena. So, have a look. Segfault. Okay. Let's see about that. You're saying it's a null pointer. That shouldn't be the case. Well, why are you giving me a null pointer? 58. What did I do wrong? What did I do wrong? Frame equals. Oh, did I not allocate a frame on the initial state, since that one I never collapsed those code paths? That will be it. Kind of wishing I had now. Okay, let's do a quick internal helper for this then. Initial state ID, that comes out like that. Push. So low level sense, a push includes all of this logic, right? Yes. Yes. Also all of this. Frame size, state ID. Frame SLL stack push. That should do the whole thing, right? And then I should be able to do this. So this is the next. This is the push. Not that one. Okay. Refresh this. Somewhere around here there's gonna be a little Stack machine program. There it is. And there we go. All right. Okay, so the game works with everything now running on this slightly wonkier frame thing instead of living in the context, right? We took it out of the context and it lives on that frame. So then what you can do, if you want to get more out of something like this, is attach stuff at the level of the frame statically as well. And of course, obviously this composes also with having multiple frames. So we could, for instance, have you might decide, and I think for this example I will decide, that I want the frame name to actually scope the symbol name. And to set something up like that, what I would do is swap the order around like this. So the symbol is actually going to be the second thing because it's sort of being subcategorized. And it's also going to be necessary to include it in the decal. And so if you did it that way, where they're sort of scoped by the frame, then all you're saying is that you're going to like stick this everywhere that we had stuck the N by itself before. Do something like this. This. Right, so now the frames tic-tac-toe underscore. Not entirely sure how I feel about referencing the symbols this way. Maybe it'd be smart to say, if you're gonna scope your, I haven't tried this before, sort of just playing around with the idea, but if you're gonna scope your symbols this way, maybe you want to wrap the reference so that you're not doing it directly on these identifiers anymore. Oops, that's not the one I want to run. And again, refresh the list, sort by name, look for stack machine, end the process, done. Okay. Well, so if that's how you set up tic-tac-toe, then the idea I wanted to show is we can do a couple things to take even further advantage of a system like this. So one is to show that we can have separate frames. Um, right? We can do something like that, and then we can do something like, so there's the frame. Do One more time. We set up a frame for a menu. Maybe here we have no need for a state. Well, maybe we just say something like this one's like this, right? Because then you're going to go right, so I'll introduce this idea of stationary as well. Stationary is just like when next points to the current state. And it's just sometimes useful to be able to say that and not have to type out the self-reference. So add it to the example. Even though it's technically redundant. So like here, it literally just nothing to do. This one becomes like this. You don't have to specify this because there's nothing to do, but you do the push. So that becomes like that. For certain reasons, you might actually still end up treating this like this, because there might be things where it's like, even though you have not changed the stack, you're still assuming this is during a valid operation where there might be something to close or wrap up after each state related to the stack. For instance, you might want to diff it, right? You might want to say, if there's been a change, let me save the change so I can keep a history of all the states. Or something like that. And so you would still more than likely want this API to always check that we have a stack. That's what I'm saying. Even though this particular case, it doesn't need to be checked. This works without a stack. Like if the stack is empty, this still works. It's technically not supposed to happen. And there are tons of evolution paths where it comes back. So I think that this is fine. Okay. Okay, and so the way that should work then is I should be able to run this. Oh, it still doesn't start in the right place. Here we go. So the new starting point should be menu Play rock, paper, scissors. Shoot rock. I should have lost a point. I should have lost a point. Why didn't I lose a point? This paper. One, two, three. Oh, but 0 is actually the scissors here, huh? Right. That should do it then. Rock. Scissors. Oh, what? Threw rock again and I lost. Well, then I throw paper. Oh no, my opponent threw scissors and I lost. This is unfair. We'll throw rock. I lost. I don't like tic-tac or rock, paper, scissors. Let's play tic-tac-toe. Not bad. Okay. Very good. Too easy. Too easy. Mr. Rock, paper, scissors. Let's do you again. Lost. Playing scissors. Keep playing scissors. Oh, I lost again. I won this round. Finally. I keep playing paper. No. No. Okay. Good. Alright. Okay. I think I'm getting into his head. Okay, I'm going 1 for 1 for him with him for a while now. Let's see. Ah, yes, you can see. There. Back to even. I quit. One other thing, the quit works, right? Yeah. Okay, so there you go. There's a little demo of building a stack machine with symbol sets. Obviously I haven't shown a super super complex system. You could like something you would really do with it. I don't know if you want to build command line arcade games or not, but there's kind of the sort of thing you can do with it. So just to review some of the main concepts, we have 2 symbol sets here plus an actual third one that's this helper Cyanit. The Cyanit helps us link states to frames through this frame ID, because we can't encode it as an ID at init time or at static time, right? At static compilation time, I can't treat one of these IDs as a static initializer, but I can treat a raw as a static initializer, and then I can convert that over here in this init path, right? And the init paths all run when I call scirun init, right? So at the beginning of my main, I can just get all of my IDs fixed up. These themselves don't need IDs. They're just function pointers, basically, to these fix-up loops. Once all the fix-up loops have happened, then these states have IDs that can be resolved to these frames, and these frames have sizes that match the type signatures that are used to structure the state functions that are tied to it, right? So we end up with all of the state functions agreeing on what the frame type is, if they all agree on their frame, and then the frame itself allocates the right amount of space for us by telling us what size we need, right? And that's the basic structure there. Then the rest is just, you know, take advantage of an arena to organize the memory of the stack in a super convenient way. And that's pretty much the main idea. You got these stack operations that you do once per state to do the state transitions. And then besides that, it's whatever you want to attach to your context, whatever you want to attach to your frame, because, you know, you can do more. Here's an example of something I didn't do yet that might be worth talking about. You could go through and say, okay, in addition to everything else we've said about frames so far, they have a type and a size. maybe we want to say that they also have, well, there's a couple important things. Let's do some advanced stuff. All right, so there's the basic frame stack. I want to show you a couple of advanced things while we're hanging out doing this. So you might want a return type off of these frames too. So you take the things that are already used for defining the frame itself and give it a second copy. These will all be called the frame return types. So now, to set up a frame, we have to have both. But anywhere that we don't really need a return, we can just null it out for now by saying void, like just set it to a default that doesn't mean much. It basically means this is the way, another way to say that might be more precise is saying return type void is the way of making the new system I'm building behave the way the old system behaved, right? This means what we already have where there is no return informationally is what all these frames are still doing. And then that should still build, right? And then you should be able to set up in your loop, right? So down here we have this loop, and we kind of want to be able to say, okay, every time we run, we're going to have a second arena called the run arena. The run arena is going to give us we're going to do an arena flipping strategy actually. So we're going to allocate a pair of arenas. And then we'll keep a little counter here that goes like this. And then at each given step, the current run arena is always the one you get at counter and 1. And then we arena pop 2. So we clear out the run arena that we're using this time. We leave the run arena from last time. And then we also keep a prev return. And so whenever you run your state function, you pass in the run arena. It gives you a return value. You store that onto the current run arena. Next time around the loop, that prev return is available, and it has its memory still intact because we set up a new run arena that's the opposite one. We have 2 of them, or 2 run arenas. So whichever run arena we put the memory on, the other one's going to be the one that we clear and are prepared to fill on the next iteration. So this is an arena flipping setup, right? 2 arenas. Every iteration you use the other one and clear it by clearing it to 0 and fill and read from the previous, right? And then what we have to do is upgrade our state functions again to make something like this work, to return a void pointer. And that means these are going to be like that. And then what we'll do is we'll put in the context, every time we do one of these steps, here we're reading the state that we need to run. Let's also say we want to store the prev return like this. Well, actually, let's put the prev return just right in the context. And there we go, right? So void prev return looks like this. And then if you have an API over here, it's like get the prev return. Then right, then you got this sort of a thing. These now all just return 0 for now because none of these actually do want to return anything. But if you ever did want to return something from, oh, you know what? I'm doing this slightly wrong. This makes, okay. No. What I'm doing doesn't make sense. What you do is not every, forget some of what I just said. It's not, I don't think I want to do this every state. It's whenever I pop that I want to be able to return. Right, so returns go back up the stack. It's when you pop that you should set a return data. And since these come from the tic-tac-toe frame, which has a 0 return size, nothing actually needs to be passed. And you're in the rock, paper, scissors frame, so you don't need to do anything. And you don't need to return anything. Okay, now what we have to do is we have to get that frame information again. Sci address from ID, state, context, stack, state ID, grab a frame from the state, and then we can say memcopy we're going to need to tell it what its run arena is before it gets this far. Context.run arena actually is what we want here. We don't want to pass the run arena in that way. It'll come through the context. Run arena. Okay, something like that kind of works. And so then you go, before we go and do the pops, so this won't work yet, but the way it would generally work is you'd go, here's my frame. I want to copy this out onto whatever memory is appropriate for saving it later, right? Whatever memory this is coming from might just be like a local to set it up, and then I want to copy it out for the next iteration to be able to see. Arena alloc, yeah, give each of these a megabyte. Okay, so that shouldn't have changed anything yet. Okay, so all of that appears to still work. So the question is, what can I do to justify attaching a return? So maybe what could happen here is that in the main each game will report whether or not you win. So like type def b32 pop something like that. So we want to return 1 whenever our player has won the game is the idea. So here's a 1, here's a 0. And then what we can do is say up here, we want to keep track of wins for each of our games, and also we'll need to keep track of the last played game or something like that. We'll need to know when we make this choice and push, when we come back, how will we interpret who won, the who won information. Okay, and so this would be like sem state decal menu record win. Frame last played game equals 1. Last played game equals 2. And that way, when it comes back, Then we increment the win counter for the last played game by 1, right? It does not do exactly what it should do, because we should also go sm context get prev return context prev return Basically, my issue is if nothing sets the prev return, then I want it to get set to 0. I probably just need to do it like this. So we set a new return there, and then we do that. So at the end of each frame, we set prev return if somebody pops during the frame or during the iteration, you could say. And so prev returns only last for 1 iteration now. Cannot run it from F2. I should just disable that. Machine and process. I did it again. I just did it again. I need to go turn that off very badly. End process. Project.forcoder. Please do not run the stack machine. Just do not run the stack machine. Load the project. There we go. That's good. Okay. So if you want to run the stack machine, come over here. And now let's try to record a win real quick. But it's still not right. What did I not do it? Record win. And then sm state next. So this is if you won and state next becomes and then the thing that's missing should go like this. Very nice. Okay, I think that's good for the return example. There's another cool thing you could do with something like this, which is you could attach serialization information to, or like logging information to the frames, so the frame can just dump its info, and then you can walk your stack and dump all the stack info that's like sort of organized into this higher level stack machine thing for you. Trying to think if I want to build an example like that though. I mean, what's the big difference between any of what I've got in that? It's like you could automate printing the board in a single place and say that you print the board between every move, but you'd have to do that for every one then. So the issue becomes, what's the context you're doing this in? Whatever you're doing it for, is there some reason to attach? I can't think of anything that motivates this with this little arcade system thingy. This is a lot more interesting of an idea when you're talking about, I mean, if these were worth logging or serializing, that would be it, but they're kind of boring. And serialization sounds like a bit of a pain. Probably not that bad. It's probably not that bad. But I don't know. I think this more or less shows the main idea. Like you go and attach special information to your frames if you want. You can also do things like create hooks that have visibility into a specific frame, and then say that your states can issue, can trigger those hooks to go off if there are states for the matching frame. So like if you have some menu hooks, then that's a hook that says, hey, I'm related to this frame, and when you execute me I can change this frame. So you got to know which instance of this frame on the stack you want to point me at before you call me. And so that would be like a frame hook. And then a state could call a frame hook without having to specify, because a state also already is the sort of thing that has a unique special frame in mind that it has access to. So you would always be able to call a hook from a state without having to specify which frame. And so you can make that the thing you're taking advantage of to organize hooks that have sort of typed access to the context. I don't know. You can sort of do whatever you want to build up a little stack machine semantics of your own design from here. I guess I'll just leave it at that, and say like, here's a generic stack machine with all the stuff you'd be used to, and if you want to improve upon it and equip it with more semantics that mean something in your context, then the rest of the creativity is up to you. But I think that's a pretty good example, right? So maybe we wrap up here. Let me think if there's anything I want to do with the symbol set stuff before I go to push it again. The main thing is that the scripts need to support building the different examples. So I guess essentially build with clang.bat. And this is like if %1 equals this. I'm not sure if this is correct. I should look up batch script syntax real quick. Here's a good example. Okay, so this looks like hopefully these work. I'll have to test them separately. I think these probably have to go separate, actually. Hopefully that works to let other people build the stack machine example. But what else could I do? Is there anything else to get ready before this goes out? Right, so there's this change. Examples, stack machine. Yeah, I think this is good. I think we save it here. Oh, let me do this separate.